Okay, welcome. Hopefully the microphone is now at the perfect noise level. First things first, before we start with a new lecture, are there any questions regarding last week's lecture? I don't think so. Okay, perfect. You know about the forum, so you can always ask questions there as well, but I will always ask whether I have questions from the previous week to start with a new lecture. Today, we will talk about data. Data is something very important in knowledge discovery in databases. It's one of the most important things, I would argue. And today, we will get to know the foundations of data. So we'll get to know which different types of data we can expect. We will get to know how we can get simple knowledge out of these data sets by taking a look at simple statistics, basic statistics. Most of these statistics you should already know, however, it's an important repetition. And we will talk about basic visualizations. So we will start with data objects and attribute types. So how can data look like, especially in a relational sense? We will talk about basic statistical descriptors, for example, a mean, a median, and things like that. These are the things you should already know, hopefully. However, we will get to know them again because there are some slight specializations you might want to know. And based on the previous semesters, I know that there are even some students that do not know a basic mean, so we will repeat that. And then lastly, we'll talk about data visualization and data similarity and dissimilarity. For chapter 4, there's a high probability that we will do that next week. However, we will try to get to that today. Okay, let's start with data, objects and attribute types. First, we have to talk about types of data sets. As I already introduced last week, there are many different types of data sets. The most common data sets we will work with are records. So we will mostly work with relational data sets in KDD, and also in the real world, you will most likely at least pre-process data to get to a relational level because they are far easier to comprehend. Relational records are pretty much databases or Excel sheets or things like that, where we have columns called attributes, we will get to that later, and rows called tuples data points, and these are pretty common and should already be known to you. We can, of course, have data matrices. Those are pretty common, for example, for PCA as well. A method we will talk about later. We are also able to work with document data, so text documents, or, and that's very important for the chapter on frequent patterns, transactional data, where we will mostly work with transactional data sets. Transactional data sets are similar to relational records, but they include an ID, and then multiple items are part of one ID. So in the transaction 1, we would have bread, Coke, and milk in here. So basically a supermarket transaction, where you go to the supermarket and put multiple things in your basket and then check out all these items at once. That's a transaction. Of course, we have other data as well, not only record data, but also graph and network data. A good example would be the World Wide Web. Multiple websites link other websites, these websites link other websites, and so on. And due to that, we have a web of websites, a graph of websites. The same is true for social information networks or social media networks, molecular structures as well, and all these things can also be mined, but with different methods. we can also have ordered and unordered data. In ordered data, we can, for example, talk about video data, where we have one frame after another frame, after another frame, after another frame. A video wouldn't make sense if we mix these frames, then we can comprehend this video. So it's an ordered data structure. We can also have time series. Time series is a pretty nice way of storing sensor data, for example. So if you have a temperature sensor outside to measure the temperature during the day, you would most likely put these sensor measurements into a time series database, where we simply store one piece of information after another. In this example, we simply have a time series of students per semester in KDD. So that's possible as well. We can have other data types as well that are ordered, but I will not get into details on them. And then, of course, we can have multimedia data. We can have data points. Oh, where's my pointer? Pointer isn't here anymore. Oh, no. As you see, video data can be ordered and multimedia data points as well, because it's ordered and it's also multimedia. A good example would be also images. As I already said, in KDD, we will mostly focus on record data. So these are our primary focus. We will get into some time series data as well, but that's a less focus in here. If you want to, for example, get to know image data and video data methods, you might want to see, take a lecture at the pattern recognition lab. Those are the experts for these kinds of data. Okay. Let's start with important characteristics of structured data, as record data is structured data. In structured data, we have multiple dimensions. Dimensions can, for example, be different attributes. So our data point chain DOE in here would have 4 dimensions. Since it has a matriculation number, it has a forename, it has a surname, it has a study program. Those are 4 dimensions. The more dimensions we have in a data point, the harder it gets to execute some of these methods, because some of them grow exponentially with every dimension, or the effort we have to input into these methods grows exponentially with every dimension we have to put in that. And that's called the curse of dimensionality. So if we have very high dimensional data, at least with less information per dimension, that's bad for us. We have to pre-process these data sets to avoid this curse of dimensionality. That's something we will do next week with, for example, PCA, the principal component analysis. Then a next problem might be that while in this example every field attribute value is filled, in the real world we might not have every attribute filled out. There might be a lot of null values, so a lot of data points that are not known at least. And that's something that is also not good for us, but happens a lot in the real world. Then a next problem is that some patterns only occur if you have enough data points to look at. That's also something that is very important for structured data. And then, if you think about, maybe a database at an online store. this database, this online store runs for the past 5 years. Okay? 2020, no iPhone 17 was sold. 2021, no iPhone 17 was sold. 2022, no iPhone 17 was sold. Until we get to 2025, once the iPhone 17 gets released, then suddenly a lot of iPhone 17s are sold. So if you look at the first tuples in the database, the first thousands of tuples in the database, nobody's bought an iPhone 17. But does that mean that an iPhone 17 isn't an item that is frequently bought these days? No, because we have to talk a lot about distribution. For example, time-based distribution, there are other distributions as well, of course. Yeah.
So, in this case, there would not be like a specific column for the 17 Pro in the past. There would be some like row that.
No, okay. I try to repeat the question, okay, just for the recording and the live stream. I think your question was whether there's a specific column or row displaying the iPhone 17 Pro. No, in structured data, at least in relational data, it would not have a specific column for the iPhone 17 Pro, but rather we would have a column. Let's say we have a column with ID, so because we want to save every thing, then we might have the customer who buys this thing, he has an ID as well, or they have an ID as well, and then we would have a column for product, where we probably have also an ID leading to that product, and for a long time, the ID for the iPhone 17, let's say the ID for the iPhone 17 is 27, this one. It wouldn't occur until a certain point of time when the first iPhone 17 would have been bought. But it doesn't have a specific column for iPhone 17. There's an important exception to that. We will have a specific kind of preprocessing later on in the semester, which is called one-hot encoding. In that case, we would have one column per product. Then we have a column for the iPhone 17, but that's something we will talk about later on once we get to one-hot encoding, because not too much information per thing. Is the question answered, or you look a little bit confused still? Okay.
Yes, it's not answered. I think so.
Yeah.
Because let's suppose in 2000, 17 Pro is not released yet. So there would not be a maybe at that time it would be like 16, 15 or 14. So there would not be the ID of 17 in that column. So there would be something in each record. It might be a 14, 15 or something else, but it would not be nothing.
Okay. No, this tuple wouldn't exist until then. So this whole row or tuple, we will get to these names in a bit, this wouldn't exist, as well as this ID wouldn't exist until the iPhone gets actually released, because we can't make things up. We can't create IDs for every product that might exist in some time. For iPhones, it might be possible because it's pretty, something we can expect to happen. But let's say, there are multiple products we can't expect that are getting released. The beauty about relational databases is that we can always create new IDs and new tuples if we get to the time where this product, for example, gets released. And then we create the product in a specific relation, so a specific table. We create so that's the product database or product relation, and there we have again an ID for the product, and we have the name of the product, and probably we have some further information, for example, the size and the weight and things like that. But we do not create the iPhone 17 until we get to the date where it gets released, and then we create a new tuple containing the ID of a new product and then the name and all the meta information we want to access with it. And only once this is created, we get to put it into the transactional relation where we store the transactions. Is that your questions answered? Okay, perfect. So that's more about databases in general. So that's something you would learn in Einführung in Datenbanken, but since it's in German, it might be hard to visit. Okay, this little excurse done, but always ask questions, that's important. That's why we're here. We get back to characteristics of structured data, or important characteristics of structured data, so the things we will have to worry about in the next days or next weeks. So distribution is pretty important. We can't just look at the first few tuples of a database and say we know everything about these databases, because it might happen that the pattern we are looking for is only in a certain range of data sets or data points. So I used a lot of different terms in the previous slide. For one thing was a data object. A data object is one entity of a bigger data set. So, for example, a data object would be this one row. That's a data object. And a data set contains of multiple of these data objects. These data objects are also known, for example, as samples or examples. They can be called instances, data points, objects, and the term I most often use, tuples. Why am I using tuples most often? Because I come from relational databases, and the term you're using most often in relational databases is tuples for data objects. But all these terms, samples, examples, instances, data objects, tuples, are pretty much the same thing for the context of KDD. There might be some exceptions. Once we get to these exceptions, I will tell you. I don't think we have to go through examples, since I've shown you one example in here as well, but it's about a simple row in a database. So data objects are described by are database rows, and they can be described by the columns. So these things to identify them further. And that's pretty much the next thing, attributes. Columns are attributes. An attribute represents a specific characteristic of a data object. For example, a customer might have a unique identifier, so an ID, name, and an address. Or a transaction might have an ID, a linked customer, and a specific product bought. Those are attributes. These attributes can also be called variables, features, fields, and the dimensions. I would say the three most important terms for the context of KDD are attribute, are feature, and are dimension. Those are used pretty often within the context of a lecture and within the context of data science. Dimension, I already introduced with the curse of dimensionality. Feature is also important for some methods which are using this terminology more often. And attribute is more or less the thing we are using in databases. It's also important to talk about how these actual values of attributes are called. These are called observations most often. I always often are also calling them values because that's more simple to do. However, observations is pretty much similar if it's an observation. That's an important thing. If we have a data object that has more than one attribute, and that's happening a lot, then it's called multivariate. If we only have one attribute value, one attribute linked to each data object, it's univariate. That might also be important if you read papers, for example, in this domain. So if you're writing, for example, data science master thesis or bachelor thesis. For attributes, we have to talk about how these attributes can be described. For example, in this case, we have a lot of numbers in attributes. Those are specific things. For this description of attributes, we have two major different views. We have a view of the statistics community and a view of the informatics community. One view is more about how these attributes are observed, and one view is more about how these attributes are stored. So let's get first into the types of the view the statistics community has. This classification is mostly based on Stevens et al. And calls about the types of measurements, so the observations of attributes. He divides measurements into qualitative and quantitative measurements. A qualitative measurement describes an attribute without providing a size or quantity. So if we have, for example, have a name, a name isn't a size. You can say Tom is better than Thomas. It's longer, but it's not a different size. You wouldn't say Tom is always longer than Thomas. While quantitative, measurements describe an objective, measurable attribute. That's most often numerical, of course, in some way, because if we can measure things, we most often describe them numerical. For example, if we measure the length of a device, that's something we can objectively measure, and therefore it's quantitative. Question: is ID quantitative or qualitative? Sorry? Okay, let's do it with raising hands. That's easier, I think. Raise your hand if you think ID is qualitative. Okay, raise your hand if you think it's quantitative. Okay, most of you think it's qualitative, and some of you think it's quantitative. It's not something we can measure. An ID is simply a term we give to these things. So we can't measure it, it only describes a thing, but we can also, instead of giving a number, we can also write A1, B1, C1. And if you do that, it's more obvious that an ID is nothing we can measure, it's more about something describing the thing. So qualitative is correct. Not every number is quantitative by definition. Most often quantitative things are numbers, but the other way around isn't true. So IDs are qualitative, sorry. Because we are not providing a size or quantity. Okay, if we now take a look at the further specifications of these things, we can even further divide qualitative measurements into nominal and ordinal. Nominal measurements are categories, dates, or names of things. So things that do not have any meaningful order. A good example would be colors. Blue, red, green, they do not have any specific meaningful order to them. Or names. Again, Tom, Thomas, there's no meaningful order to them. We can also talk about martial status. We can talk about occupation, study program. Those are things that are nominal. Because they do not have any specific order to them. On the other side, before we get to the special case of nominal measurements, we have ordinal measurements. Even though we can't measure things, it might happen that they have a meaningful order to them. For example, a size we can't specify by measuring, but we can measure by estimating. It's still a qualitative measurement because it's not objective, but it has a meaningful order to that. A small thing is smaller than a medium thing. A medium thing is smaller than a large thing. So ordinal measurements have a meaningful order to them. Other examples might be grades, army rankings, and so on. So whether a major or general or things like that. So we can further divide qualitative measurements in nominal and ordinal measurements. I skipped over the special case of nominal measurements. There are some cases where we have binary measurements, where we only have two possible states. For example, so 1 and 0 or true and false, those are binary values. An example might be the traditional sex, male and female. Of course, if we are talking about gender, that's a different thing. But for sex, male and female only has two outcomes traditionally. But we can also talk about medical tests, positive or negative. We can talk about passing an exam. We can have yes, we can have no. We can have day and night. We have day and night, for example. Those are special cases which often happen with nominal measurements. And they still have no meaningful order to them. A male and a female, none of these things is better or worse. So there's no meaningful order to them. Night and day, we can start with a day, we can start with a night. That's not important as well. Yeah. So that's a special case that might happen with nominal measurements. Now we can go back to the Stevens classification. We can also have quantitative measurements being split up into two different types. Because we can have interval data and ratio data. For interval scaled measurements, so interval data, we measure things on an equally scaled unit scale, where we do not have any true 0 point. Of course, values have always an order with quantitative measurements. A good example is Celsius or Fahrenheit. In these cases, if we walk up from 0 to 1 degree, it's the same difference in degrees, Celsius, for example, as if we walk up from 44 to 45 degrees. It's the same difference in things. Decibel, on the other side, is a logarithmic scale, so we do not have the same things. And most important, we do not have a true 0 point for Celsius and Fahrenheit. So if we are at 0 degrees Celsius, we can still go lower. If we are at 0 degrees Fahrenheit, we can still go lower. Of course, at some point, we won't get lower. So I think with Celsius, it's about minus 273 point whatever degrees Celsius, but it's not at the same point as 0. That's the important thing. With ratio-scaled measurements, we have an inherent 0 point. So 0 in the scaling also means the lowest point we can get to. That's true with Kelvin in temperature. 0 degrees Kelvin equals to, I think, minus 273 point whatever degrees Celsius, and is therefore an inherent 0 point. And these are scaling differently most often than interval scaled measurements. So the best example in this case is, of course, temperature, because we have two measurements pretty often used, which are interval scaled, and one measurement which is used in science a lot, which is ratio scaled. That's basically the Stevens classification. Do you have any questions about the Stevens classification? Yeah. So your question was, I repeat it again for the recording, your question was about grades. And you say grades are somewhat qualitative as well. Yeah, that's somewhat true. However, you can't really measure them objectively 100%. You can maybe talk about points in exam. Those are pretty much objective, where we tend to go into the quantitative domain. But for example, KDD, we have a certain point scaling. So we have normally 50% of points is passing grade, and so on. We have a specific thing in here, but there's a specific rule in the examination rules that if a certain percentage of first try students in the exam has a point average below whatever, it's very complicated, then we have to lower the passing grade. So it moves a little bit. And therefore, depending on the overall thing, the grade isn't objectively, but it might change on the based on the students participating in this exam. And therefore, it's not 100% objectively. And therefore, it's more a qualitative measurement than a quantitative measurement. If a grade is determined 100% objectively, without influence of other factors, then we can talk about it as a quantitative measurement. Okay? And so it's still objective, of course, but you are dependent on other students a little bit. So the worse the other students do, the better for you. That's complicated. You can read it up in the examination rules, but yeah. Or we can talk about it right before the exam. That's also fine for me, but not now. Our questions, yeah. Oh, sorry, yeah, yeah.
Yes, ratio scale in real line. So in this temperature in Kelvin, it cannot go below like this 0 point.
Yeah.
Or
Kelvin doesn't have any values below 0. So the question was whether Kelvin can go below 0. It doesn't. That's just physics, or by definition, it's at the absolute 0. So Kelvin is defined in that way. Our questions? Okay. Then we can go to the next view on attributes. Yeah.
So it's just about the scaling type of data. You know, we don't have any, for example, any tangible other example that we have for ratio scale. I think it just happened for the scaling. You know, for example, we have kilogram and pounds or something like this, which also is in this category.
Okay, we can talk about whether we have where to put kilogram and pounds, for example. Where do you think we put kilogram and pounds in this domain?
we can put kilograms in ratio scale.
Why?
Because there is a like 0 point.
Yeah. If we take a look at kilogram and pounds, normally we have an inherent 0 point. You can't weigh below 0 kilogram. You can't weigh below 0 grams, pounds. That was the next example. So the inherent 0 point talks about being ratio scaled. Of course, yeah. Okay. Okay. The other view on attributes is by the informatics community. As I already said, it's more about how we can store data. That's the view. Because of that, we are dividing attributes into categorical and numerical kinds of data sets. Categorical data is everything that is not numerical, more or less. So, for example, we have names, we can have, everything that isn't really a number, and it's most often about strings. It mostly corresponds with qualitative measurements. It mostly corresponds with qualitative strings. On the other hand, we have numerical data. Numerical data are, for example, integers, floats, and things like that. These are mostly corresponding to quantitative measurements. Why I'm saying mostly? Well, because we had an example in here. If we now remove these letters, then we are again, of course, numerical, but we are still qualitative measurements. So there is a world where we have, okay, that isn't possible to happen. We can't have the same IDs. No, it's possible. We can have numerical but qualitative measurements. But most often those two correspond to each other. If we are talking about categorical data, we do not further divide these things, at least in our context in KDD. For numerical data, we can talk about two different things. We can talk about continuous numerical data and discrete numerical data. Continuous attributes have real numbers as attribute values. So, for example, temperature. We can go in any detail on there. Between 23 and 24 degrees Celsius, we can still have 23.5 degrees Celsius. And between 23.5 and 23.6 degrees Celsius, we can still have 23.55 degrees Celsius. We can always fit another measurement in between. So we are continuous. Of course, and that's an important distinction, our storage and also our sensors have limitations. We will not get into the 100th point after the comma. There's a certain level where we stop. However, if it would be theoretically possible to go even further, to even be more continuous in there, we still talk about continuous attributes. Even if due to sensor limitations or due to simply programming restrictions, we can't divide it further. Simply if the value we measure is continuous, that's enough for us. Of course, the stored thing is represented by a finite number of digits. Continuous attributes are most often represented by floating point variables, so floats, doubles, things like that. Or reals, that's also possible. On the other side, we have discrete attributes. Most have a finite, countable number of elements. A zip code has a limited number of possibilities. We can go further. A set of words in a collection, that's not very good example because it's not numerical, but let's go with another example. I have to change that. Everything that has a set fixed number of possibilities is discrete because we can't continuously split it up anymore. They are most often displayed as integer values. However, you can also have float values for discrete values if we have a certain specific number in here. We again have a special case, binary attributes. Those can be 0 and 1, and therefore they are also discrete numbers, discrete numerical attributes, but they only have 2 possibilities. So here we see that the qualitative and the numerical attributes have some overlap as well. Okay, so that's basically about the view on attributes. We can talk about these things very often, and I have to admit, I often put a task in the exam where I give you an example of a data set, and you have to put these things, or a certain attribute, into this classification. So that's something that is pretty easy to check, where we have understood these 2 classifications. So are there any more questions about that? Yeah. Sorry? So temperature, this one here. So your question is whether we can, how we can divide something? That's how can we divide something through zero? We can't divide something through zero due to mathematical limitations, but I'm not sure why this is needed to be divided through zero. To have an inherent 0 point, it doesn't have to be divided through zero. It's just so we have an absolute 0 point. So a point where we can't get below. That's the definition of a ratio-scaled attribute. If we can't get below 0, we are ratio-scaled. I'm not sure why we should have to be able to divide through 0, because you can compare I know that my definition of Kelvin is correct. By the way, depending on the definition of the different measurements, so Kelvin and Celsius and things, you might have to just add things. So in this case, we simply have, it depends a lot on the measurement, how these things are calculated into each other. If you compare US dollars and euros, the calculation is different than if you compare yen to euros. So depending on the type, we have to perform different calculations. I can't even say what the calculation of of Celsius to Kelvin is, to be honest with you. I only know that minus 273.15 degrees Celsius is 0 Kelvin, not 0 degrees Kelvin. You are not expected to perform any transformation in the exam on that in KDD. If you are in any physics course, it might happen that you are required to do that calculation, but not in KDD. So I can tell you about that. It's just an example to visualize these things. You do not have to be able to calculate water freeze temperature or things like that. Do not learn that. Do not put that onto your cheat sheet. That's not important. If that's the question. And I can't tell you anything about that. I just looked it up once I created these slides, or in this case, Mrs. Siegel, my colleague from 3 semesters ago, created the slide, but I can't tell you about it. Okay. And that's not important for the exam. All these things are just examples to visualize things, yeah. Other questions? Yeah.
What about currencies? Are they, if you compare them visually, they can be infinite possibilities?
So are we talking about ratio scaled versus interval scaled, or are we talking about more about numerical continuous and okay, continuous and discrete. So the question was, I have to repeat it again for the recording, where we have to put in currencies in this case. Well, it depends a little bit. If we are talking about currencies, you can hand out during a transaction in an online shop, in an offline store, whatever. Those are most likely discrete because we can only go to 2 points of after the comma. However, if you look at currency exchange rates or at the Nasdaq or whatever, at the DAX, where you trade certificates and things like that. Those are most often even given in 15 points after the comma. So in this case, we are talking more about a continuous implementation. So it depends a lot on your use case. You have to think about what's the reason in your use case? Have we a specific certain amount of values we can expect when it's discrete? If we are more talking about a continuous thing, we are more likely in the we have a lot of values that can even be divided further and further and further. Then we are more in the continuous spectrum of things. So there is no definitive answer to that. It depends a lot on the use case. Question answered? Okay. And that's true for many cases in KDD. We have to take a look at the use case. That will happen a lot, and that's often my answer to questions. That's why we have the exercise, where we can talk about some use cases. But in practice, a data scientist most often needs an expert to talk to. An expert that can explain how things work in this specific domain. And that's something that happens very, very often. You can just ask questions. You do not have to be an expert of every domain. Most often you get an expert with time being in a certain domain, of course, but most often you have an expert who knows about things and you are more about analyzing the data the expert can explain to you. Okay, then I think we can get to the basic statistical descriptors of data. So, just a disclaimer, it's very basic. I hope that most in here know about these statistics, but we still have to go over them. And based on examination results, where I often ask for a mean or median or things like that, those tasks get not solved that well, so please make sure you know about them. Basic descriptors of data are very important to better understand the data. They are not gain knowledge, so it's not doing a basic statistic analysis, test on data is not data science by itself, but it's necessary to get to know the data and to be able to further analyze the data to really gain previously unknown, interesting patterns from these data sets. There are many characteristics, for example, the median, the mean, the max, the minimum, some quantiles, outliers. Outliers are more difficult, and we will talk about them in the last lecture of the semester as well, and variance and things like that. Most often we can perform these statistical descriptions on numerical attributes. There are some we can also perform on categorical attributes. For example, we can count how many different values we have. That's also a basic statistical description of categorical data. However, most of these descriptions need numerical data in some way. And we will talk about numerical data primarily here. These numerical things can, for example, describe data dispersion. And box plot analysis we will get to later on, and a quantile analysis can, for example, show us sorted intervals in this data. So we are often talking about dispersion, how this data is structured in a certain interval. Before we can get to the real statistical descriptions, we have to talk about an important distinction. Population versus sample. If we're talking about a population, when we are talking about every single data point in existence for the specific reason. So, for example, if we're talking about the population of FAU students, we are talking about every single student enrolled at FAU, whether they are present at FU, actively studying or not. We're talking about everyone. The population of KDD participants are all students enrolled in KDD, not only you in the lecture hall in here. You are a sample of KDD students. You are a certain subset of the population of KDD students that came here to listen to the lecture. The population size is often described by a big N. So if you see a big N, we are talking about all elements in a certain population. It's very hard to define and observe all populations most often. For example, to get to know the population of Germany, you would have to perform an exhaustive population study where you do not miss any single person living in Germany. And that's most likely not happening. We have babies and things like that that aren't even registered yet, and that's not feasible often. While a sample is very feasible in most cases. The sample is the thing you most often do. You pick a certain selective and hopefully representative subset of a population that you obtain by a sampling method. The sampling method often determines whether we are really representative or not, because if you have a shitty sampling method, then it's not representative. Again, for KDD students, you are not a representative subsample. By taking a look at the past semesters, I know that more students in here will pass the exam than in the overall population of KDD students. Because you come here at a Wednesday morning to listen to my lecture, and you are involved in KDD. So you are more likely to pass the exam, but therefore you are not a representative subset if I will perform any study on KDD students in here, because you are very engaged in the lecture, or at least engaged in the lecture. That's not a representative method of sampling. The sample size is not described by a big N, but a small n, and you would like to avoid sample biases. For example, you in here, you are more engaged than the others, therefore it's a sample bias in here. Samples are very faster and less costly to obtain because you only have to take a look at a subset, and also the methods that we can later apply on the samples do not have to work through as much data as if we would take a look at the population of data. And we have more control regarding missing values and outliers. Most often you would like to avoid these things. With one exception, there are data science projects where you specifically want to get to know missing values and outliers. Then, of course, you have to have them in the samples as well. Okay, the first and simplest, or one of the simplest methods, statistical descriptions to get to know the central tendency of a numerical attribute is the mean. In this case, the mean most of you might know is the arithmetic mean. The arithmetic mean simply sums up all numerical values you have at hand, adds them up, and divides them through the number of samples. It's very sensitive to extreme outliers. So, for example, what's the mean of these three values? 2. Pretty simple. If we now have these three values. When suddenly one value drags the mean up very much. So we end up at 102? Yeah, 2. Yeah, exactly, 102. So we are very sensitive to outliers. Of course, with 3 values, we can't really talk about outliers. It has to be more values, but just for the sake of an example in here, that's more important. If we want to avoid to be sensitive to outliers, we can also talk about the trimmed mean. The trimmed mean is a more complicated formula where we take a look at a certain interval of data within the data set. And we simply exclude the lowest and the highest x% of data. So if we would have -10, 1, 2, 303, -100, and we would opt to exclude the lowest 25% and the highest 25% when we only look at 1 and 2 in the trimmed mean, and then calculate the trimmed mean the same way as we have done the normal mean for the values in the interval we are taking a look at. And more or less, that's what this formula is about. We're simply discarding the lowest and highest x% of data to avoid having outliers in that calculation. Very important, if we are talking about a 50% trimmed mean, so we cut off 50% of each side, then we are ending up at the median. The median is the next central tendency measure we are talking about. While the mean is determined by a calculation, so adding up all values and dividing them through the number of values we have at hand, the median is about how many values are above and below a certain thing. So for our original example, or not the original example, but this example in here, what's the median in here? 2. Because we have 50% of values lower and 50% of values higher than this value. The median gets somewhat tricky if you have 4 values at hand. So if you have 1, 2, 4, and 303. What's the median in here? 3. Exactly. Because now we have to take a look at the 2 values in the middle and then have to calculate more or less the mean of these 2 values, or the average of these 2 values. That's what is defined at the row here. If we have an even number of values, then we add up the 2 values in the middle and calculate the average of both. The median is more robust to extreme values and outliers than the mean. However, we might end up, in some cases we might end up with the same value, and in most cases we end up with a different values for mean and median. We will have a picture for these 2 things and the impact on central tendency later. But for median, we can also talk about the central tendency for interval grouped data. Interval group data is data sets where we already merge data sets into more compact things, aggregated data sets into more compact data sets. In this case, for example, we simply have a data set which is about ages, where we have a class for the age group 1 to 5, a class for the age group 6 to 15, and so on. And we get provided the absolute frequency of data points in that class. So we know that 200 persons are within the age group 1 to 5. We know that 450 people are within the age group 6 to 15, and so on. And now we want to know where the median in this dataset lies. The answer is already given, but how can we derive that the answer is given in here? Well, we first have to take a look at the absolute frequency. We simply take a look at how many people in percent are within each age group. So 300 people of 3,194 equals to about 6% of people. While 300 people of 3,194 equals to about 9.3% of people. If we now add up this frequency from the lowest to a highest group, we can get the cumulative relative frequency. So we know that about 6% of people are at most 5 years old, then 20% of people are maximum 15 years old, 29.7% of people are at most 20 years old. Below 50, we have 76.7% of people. And now we are at a point where we know that the median has to be in class 4, because we have for the first time surpassed the 50% range. Once we for the first time surpass the cumulative frequency of 50%, we know that in this class we are in the median group. Is that logical? I hope so. Now we know that the median is somewhere between 21 and 50 years. However, that's a big range. We can also, so that's simply the process I just explained. I will not go into details in here because we are somewhat behind. We can also calculate an estimated median within that group for these things. It's an estimation, and it assumes that we have a very much flat distribution of ages within the group. However, if we assume that, we can then calculate the approximate median within that group. And that's done by taking a look at this formula, where we take a look at the lowest boundary. So in our case, the lowest boundary is 21 of a group. Then we add 1/2 of the sum of all absolute frequencies minus the cumulative sum of absolute frequencies below the group. So in this case, these two values. And then divided through number of values in the group. In our example, we end up, not in the group, up to that group. We end up with 33.94 years for our example. Of course, that's a calculation that it's hard to be done in the head, so do not expect this calculation to be done in the exam. That's too hard for the exam. Just to give a little example of what's too hard. The calculations of median and mean both are things we can expect to do in your head. You can be expected, of course, to determine in which group we are. Are there any questions about that? We have to have time for that. Okay. Then we go to the last central tendency method, the mode. The mode is the value that occurs most frequently within the data set. So in this example, we do not have a single value that occurs most often, because 1 occurs one time, 2 occurs one time, 4 occurs one time, 303 occurs one time. So by definition, all of these occurring most often, all of these become the mode. If we now modify our data set to include the second 2, the second 2 makes the 2 the most often occurring data point, and therefore 2 would be the mode of the data set, or the attribute. There are different names for different quantities of modes. If we have only a single value being the mode, then we are talking about a unimodal attribute. If we have 2 values being the most often occurring things, so for example, in this data set, where we have 2 2s and 2 4s, it would be bimodal. And in the original data set, where we have more than 2 values being the mode, then we are a multimodal data set. It's somewhat a definition thing whether we are really calling all of these values a mode, because if every value is only occurring once, you wouldn't really call them a mode, because in this case you would simply say there is no mode, every value just occurs one time. However, let's say if we have this, then we are really multimodal. Yeah. Yeah, exactly. So that's the last method of central tendency. If we take a look at these central tendency measurements, we can also determine a dispersion of data. Yeah, do you have a question?
On like previous slide,
Hmm?
in our like the original data set 1, 2, or 303, it's like no mode exists.
Yeah.
So any if values more than 3,
Hmm?
like in this data set, it's multimodal.
Yeah. So the question was whether the original data set, so this data set, I have to repeat it for the recording, is really multimodal. No, it isn't, because you would say this is not containing any mode, every value only occurs once. But in this case, we have 3 modes, and not everyone is only occurring once. So by definition, this would be multimodal.
Like if we have more than 2 modes, then it's
Yeah,
multimodal.
exactly.
If it's all values are unique, then there is no.
Yeah, if all things are unique, then there's no mode. By definition. Exactly. Okay, using the mode, the median, and the mean, we can talk about skewed data distributions. We can, for example, take a look at a perfectly distributed, or not perfectly distributed, a normal distributed data set. There are different kinds of distributions. For example, a normal distribution. We might talk about other distributions that are very often assumed in statistics later on. The normal distribution is created by using this formula, containing the variance and the mean. We will do that later on specifically, but a normal distribution pretty much has the median, the mean, and the mode at the same point, just right through the middle of the distribution. So they are at the same point. In most cases, we do not have a perfectly distributed data set. We have data sets that are somewhat skewed in one or the other direction. And then we have two different kinds of distribution. We can have a positively skewed data distribution and a negatively skewed data distribution. A positively skewed data distribution has a lower median than the mean in most cases. While a negatively skewed data distribution has a mean lower than the median. And by taking a look just at these two things, we are determining whether we have a positively or negatively skewed data distribution. The mode is somewhat critical in here, because if we have a univariate mode, there's a high likelihood that it lies below the median for the positively skewed data distribution. But it's not a 100% guarantee, because we might also have a value like, let's say, we have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, whatever, and point. And at some point we have 101, 101, 101 in here. But the mode and things are whatever at 22, and not the mode, the median and the median. The mode is at 23, and then not the mode. Mean is at 23, and still, in this case, the mode would be 101. The probability is just higher that it's in the lower range, because if you have multiple values, multiple same values, it drags the skew down in the value range. So there's a high likelihood for that being the case. So positively skewed data distributions are more likely to have a mode below the median, not 100% given. Yeah. I think this explanation was a little bit flawed, but I hope the example helps out a little bit. Yeah. Okay, you didn't understand. Okay, let's say we have a positively skewed data distribution has a lot of values, a value bump below the mean and the median. So there are more a higher number of values below the mean and the median at some point. So we have, maybe I should do a real example. Let me come up with a real example. We have 1, 2, 3, 4, which is pretty much this way. Then we have 5, 5. So we are going up in here, and then we go down at some point. If we take a look at the values themselves, then of course a distribution where we have 8, 8, 8 would have a second bump in here, and therefore it's obvious that the mode is above the median. So let's say the median is here and the mode is here. The median and the mean is here. Sorry. However, most often these curves are not done on a per value basis. They are more averaged out. So we put a lot of values into one bin to gain this value range. And now let's say we are having, that's not visible enough. I'm drawing a perfect normal distribution instead of drawing what I want. So that's a skewed data distribution in some way. Due to putting values into bins, it might happen that the mode still is here if you put things into bins, because maybe the bin is, well, let's say 80, 80, 80. The bin is 70 to 90, and these are the only values within that bin. But the mode is still within that bin, because we have the most values that are 80. That can happen with a thing like this. Maybe we should do that within the exercise in a little example to have more values at hand, because I can only draw so many values in here. I will try to come up with an example for the exercise where we can really take a look at that. Okay? I think that's better when doing it here. But let's say the mode is not 100% guaranteed. In 99% of cases, it's below median and mean for these cases. And if you have a per value drawing, then it's always guaranteed that it's lower, because then we wouldn't have the bump. For normal distribution curves, we are talking about this formula again here. We are talking about a normal distribution which guarantees us certain things for value ranges. As I already said, we have the mean and the standard deviation as part of this formula. So we have the mean and the standard deviation to create that formula, and we know that within the interval of mean minus standard deviation to mean plus standard deviation, so this interval in here, we have about 68% of all values being present. That's always the case for normal distribution, by definition. We know that for the mean minus 2 times the standard deviation to the mean plus 2 times the standard deviation, about 95% of values are present. And the same thing is with 99.7% for 3 times the standard deviation. This can be used to, for example, determine outliers. Because if we say 95% of values are within that 2 times the standard deviation range, then we can make sure that everything outside of that, if we say 5% of highest values, or 2.5% of highest values, 2.5% of lowest values are outliers, then we simply get to know them. That's not the perfect way of doing things. We will talk about that in the outlier lecture. Yeah.
It's like that example when you close the boundary and left the outsides. Like in this example, minus 1.
So the trimmed mean, yeah. The trimmed mean would be an example where, so it's also about trimming. It's not the same case in here. It's, yeah, yeah, you can say that. If we are talking about 2.5% of trimmed mean, then we would do this thing here.
My question is that when we are multiplying the standard deviation, we are narrowing down to our
Yeah, in most cases, we not narrowing that down. It's more about properties of a normal distribution where we talk about here, because it's guaranteed that we have about 95%, it's not exactly 95%, but about 95% under the surface of this thing, then we know that within that range we have the most values, 95% of values. And while we most often do not have a perfect normal distribution in the real world, it's very often that we are close to a normal distribution, and therefore we can somewhat estimate that these properties are also true for a certain sample or population that is close to a normal distribution. Yeah, that will get important later on in the semester, more often, where we assume a normal distribution. At least, especially with statistical methods, for example, in classification and things like that. One thing we do not talk about, or did not talk about yet, but should be known to most of you as well, are the variance and the standard deviation. The variance is about measuring how much most values differ from the mean. That's description, rough description of these things. Where we talk about, again, summing up all values, minus the mean, squaring up, and then dividing it through n, the number of values, minus the mean, minus 1, sorry. So we determine the average deviation from the mean squared. That's the variance, basically. X with a thing here is the mean in here, and x1 is the concrete value we are taking a look at. N is the number of samples, as we always had before. So we have the squared deviation from the mean. And basically, that's why we can take the variance and taking the square root of the variance to get to the standard deviation. Because previously the variance was squared, and if we want to have the non-squared variant of that, then we have to take a square root and we end up with the standard deviation. So the real value, how much is the average value differing from the mean? That's the standard deviation, more or less. These things are also often used in our dataset and will be necessary as well. We will have examples for that in the exercise. There are also other things, and I do not think that we can get through them, but just a little preview for next week. We will start at this exercise sheet as well. So I have not exercise sheet slide. And then next week again. So remember me that we have to start at 23. But we will talk about things like range, quartiles and quantiles, which are pretty similar to, linked to the median. To be precise, the second quartile is the median. And we will talk about box plots that week, which can be, for example, used to determine a simple outlier method. But that's too much to do right now, so we will continue next week. Unluckily, I didn't get that far into the lecture as I thought, but we have enough buffer to do that, so that's not a problem. I'm very happy that we have a lot of questions, that's very good, but of course it extends the lecture a little bit. Okay, have a nice time, see you again next week at the same time, at the same place.